Hello everyone. In the next lecture of thermodynamics, we're going to discuss Gibbs-Helmholtz equations. We know the third fundamental equation of thermodynamics for a closed system, which is dA equals to minus VdV minus SdT, which has just been derived in the previous lecture number 31. And if the volume, this parameter, is kept constant, then this equation can be written as what? This is vanishing for at constant volume, then this dt term would go to the denominator here, and since the volume is kept constant, then the differential terms would become partial differentiation terms. That means del A del T V equals to minus S. Okay, so del A del T V equals to minus S. Now we know that the actual expression of A is U minus TS. Let's put the value of del A del T V in place of minus S here in this equation. Here it is U plus T into minus S actually. So in place of minus S we can put this value. Okay, del A del T V. This way we get this relationship, U plus T into del A del T V. Actually del A del T V is nothing but minus S. So in the definition of work function A, or Helmholtz free energy A, we can put the value of minus S as a function of variation of A with respect to temperature at constant volume. This way, this is the first Gibbs-Helmholtz equation. This way we will get 5 more equations. We have another equation number D, which is dG equals to V dP minus S dt. The same way our approach should be. Okay, that means here, in order to send this dt into the denominator and make this parameter vanished, we have to keep the pressure constant. So at constant pressure, what happens? It would become del G by del T at constant P equals to minus S, and this minus S should be replaced by that partial differentiation term in the definition of G, which is H minus Ts. So this is actually H plus T into minus S. So in place of minus S we are putting this parameter, okay, del G del Tp, and thus we get the second expression of the Gibbs-Helmholtz equation, G equals to H plus T into del G del Tp. Equation 1 and 2 when are rearranged. So let's go back to equation 1. Okay, this is equation 1. So if this is the equation 1, then U can be taken to the left hand side, so you will get A minus U, and this T, when go to the left hand side, it will go to the denominator, so you will get the result A minus U over T. So del A del Tv is nothing but equal to A minus U by T. On the other hand, here in this equation, take this H into the left hand side, so it would give you the result G minus H, and then take this T to the left hand side, it will go to the denominator, so it would give you the result G minus H by T. So this way you would get equation number 3 and 4. Okay, del A del Tv equals to A minus U by T, and del G del Tp equals to G minus H by T. Now if this G is the change in G and if this A is the change in A, then here these parameters would also be the change in A minus change in U, change in G minus change in H. What type of change? No, it is finite change. That means delta. Okay, so for a finite process, instead of A, if you write delta A, then instead of A minus U, you can write delta A minus delta U. Okay, this way you are getting equation 5 and altogether equation 6. Altogether 6 number of equations here. Okay, this is del of delta G with respect to delta T at constant pressure equals to delta G minus delta H by T. Okay, these types of equations will be applied in thermochemistry or in all chemical applications such as chemical equilibrium or in other chemical kinetics, so many places. Okay, so these are having immense importance in chemistry. That is why this gives Helmholtz equations. So equation 1 and 6, 1 to 6, that means there are altogether 6 equations. These are all the different forms of the Gibbs-Helmholtz equations. Now some implications of Gibbs-Helmholtz equations. Okay, we have four implications here. First of all, we have to evaluate the value of del A by T over del T at constant volume. So what is the value? Just put this value here and then differentiate first A and then 1 by T. Okay, if you differentiating A, then keep 1 by T constant. Second time, if you are differentiating 1 by T, then keep A constant. So first we are keeping 1 by T constant, then differentiation of A with respect to T at constant volume. And second time, when we are differentiating 1 by T, then A is kept constant, so it is differentiation of 1 by T with respect to T at constant volume. The result is here. In place of this, we can put the value. This is equation number what? This is equation number 3 from the Gibbs-Helmholtz equation. Del A del Tp is nothing but A minus U by T. So we are putting this value here. We are mentioning this also. And here, simple differentiation. The differentiation 1 by T with respect to is what? It is minus 1 by T square. So it is minus 1 by T square. Okay. And the result is A minus U, this one, by T square minus A by T square. And finally, their combination gives you the result minus U by T square. So definitely these two, both of them are state functions. So minus U by T square is also yet another state function. So this parameter is actually a state function. So in the exam, you are given to solve out whether this is a state function or a path dependent function. So the answer is this is a state function. Okay. Now let's evaluate del of G by T with respect to del T at constant pressure. So simply just 1 by T constant, differentiation of G constant, differentiation of 1 by T. The result is 1 by T into G minus H by T, because del G del Tp is nothing but G minus H by T, equation number 4, and here G into minus 1 by T squared. So final result is minus H by T squared. This is yet another state function. Let's evaluate A by T with respect to 1 by T at constant volume. Okay, so simply differentiate. This is a little bit complicated, not so much simple as the previous two, 1 and 2. So 1 by T constant, differentiation of A, and then A constant, differentiation of 1 by T. Okay, this value is nothing but T square into S. So how do we get this value T square into S? This value, okay, let's find out. And this value is 1, so A into 1 equals to A. Okay, so finally we have got T square S by T, that means Ts plus A, isn't it? So here we are showing here, just take the reciprocal of this relationship. This is del A by del 1 by T at constant volume. Instead of that, we are taking its reciprocal. That means del of 1 by T with respect to del A at constant volume. So in that case, 1 by T is minus 1 by T square. Since T and A are different, so it is del T by del A V. Now this one is minus 1 by T square del T by del A V. So definitely its reciprocal del A by del 1 by T V must be reciprocal of this one also. So this is minus T square del A by del T V. So minus T square del A by del T V. Okay, but this one, you know, energy by temperature is entropy. So, and this is definitely minus S. So minus S into minus T square equals to T square S. Okay, we know that del A del Tv equals to minus S. So we are putting here, this value is again a state function. Similarly, when we are going to evaluate del of G by T by del of 1 by T with respect to at constant pressure, then also the same results are obtained and we get the final result Ts plus G. And since G equals to H minus Ts, therefore Ts plus G must be equal to H, which is yet another state constant. So that's all for today's lecture. Thank you. Have a nice day.